This video looks at equilibrium constants and equilibrium expressions. By the end of this video, you should understand the difference between the equilibrium constant, the equilibrium expression, and the equilibrium position. You should be able to write an equilibrium expression for a reaction. You should be able to calculate the equilibrium constant for a system given equilibrium concentrations. And you should understand the significance of the relative size of the equilibrium constant. Let's start with some lingo that's important to this video. First, the equilibrium position. This represents the set of equilibrium concentrations, meaning the concentrations of all reactants and all products at equilibrium. The equilibrium expression is a mathematical expression which shows the concentrations of products raised to their coefficients divided by the concentrations of the reactants raised to their coefficients. When writing an equilibrium expression, it's important to note that we do not include solids and liquids. We only include gases and aqueous solutions. There's two reasons for this. First, solids and liquids don't have concentrations that change significantly throughout a reaction. Furthermore, the amount of solid and liquid in a reaction system does not affect the rate. Soon we'll see that the equilibrium expression is derived from the rate law, and since solids and liquids have no effect on the rate law, we won't include them in our equilibrium expression. Taking an example, here the small letters A, B, C, and D represent coefficients and the large letters reactants and products. Our equilibrium expression would then be the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to their coefficients. If we solve this equilibrium expression, the value we obtain is the equilibrium constant. Generally, we do not write units on our equilibrium constant. Also, please note that this is big capital K for equilibrium as opposed to small lowercase k for rate laws. It's easy to get these two confused, but they're very different things. Let's look at how to derive the equilibrium expression and constant from our rate law. This is not a derivation you'll have to do, but it's important to understand where these expressions come from. Consider this simple reaction shown here at equilibrium. If we write the forward reaction separate from the reverse reaction, we see that it's an elementary reaction, meaning it occurs in a single step. So we can write a rate law directly from this reaction, which would take this form. We can do the same for the reverse reaction. So now we have a rate law for the forward reaction and a rate law for the reverse reaction. As we know, at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. Therefore, I can set these two rate laws equal to one another. If we rewrite this with some algebraic manipulation, we obtain this expression here. Since the ratio of the rate constants is constant at a particular temperature, dividing a constant by another constant gives us a new constant. This constant, our equilibrium constant, is equal to this expression here. The concentration of products raised to their coefficients divided by the concentration of reactants. So in sum, the equilibrium constant depends only on the stoichiometry of the reaction and not the reaction mechanism. Therefore, we can get the equilibrium constant and the equilibrium expression directly from the balanced equation. This is called the law of mass action, and again, it tells us that the equilibrium constant is equal to the concentration of products raised to their coefficients over the concentration of reactants raised to their coefficients. Up to now, we've been using KEQ to represent equilibrium constant. We're going to look at many types of equilibrium constants in this class, but for now, let's focus on two. Kc is our equilibrium constant in terms of concentration, and Kp is our equilibrium constant in terms of partial pressures of gases in a system. We'll start by looking at how to calculate Kc. Consider this reaction here. When studied at equilibrium, it's found that the concentrations of the reactants and products are as shown here. This set of concentrations is called our equilibrium position. Pause the video and see if you can write an equilibrium expression for this reaction. Then plug in the values and solve for our equilibrium constant. Welcome back. Here's our equilibrium expression. Plugging in values, we obtain an equilibrium constant of 4.36. Now let's look at an equilibrium expression involving pressure. When dealing with gas phase systems, it's common to express partial pressures instead of concentrations of each gas. In this case, our equilibrium expression is written the same way. The only exception is instead of brackets to represent concentration, we use large P to represent partial pressure. This would read the partial pressure of gas C raised to its coefficient times the partial pressure of gas D raised to its coefficient, and so on. Here's a gas phase reaction. Pause the video here and write the equilibrium expression, then solve for the equilibrium constant using partial pressures. Welcome back. Here's our Kp expression. Be sure that you used capital P instead of brackets. And plugging in values, we get a Kp of 1.9 times 10 to the third. Some important notes about Kp and Kc. Kp does not equal Kc. Recall that at a given temperature, the partial pressure of a gas is proportional but not equal to the concentration. Here we've used the ideal gas law and rearranged algebraically to solve for concentration. We see that the partial pressure of A, again, is not equal to the concentration of A, but it is directly proportional. This means it's very important to be clear whether you're using Kc or Kp when writing equilibrium expressions. So what does the value of K mean? Well, in situations where we have a very small amount of reactant and a very large amount of product, we'll have a large numerator and a small denominator. This will result in a very large K value. In situations where the K value is much larger than 1, we say that the reaction is product favored, meaning that at equilibrium we have a lot of product and a relatively small amount of reactant. In terms of equilibrium position, we can say that the equilibrium position lies far to the right. On the other hand, if we have a large amount of reactants and a small amount of products, we'll have a small numerator and a large denominator in our equilibrium expression, resulting in a small value of K. When our K value is significantly smaller than 1, we say that the reaction is reactant favored, meaning that at equilibrium we have a large amount of reactants and a relatively small amount of products. Again, we could say the equilibrium position lies far to the left. It also tells us something about the extent to which the forward and the reverse reactions have proceeded by the time we reach equilibrium. In a products-favored reaction, the forward reaction has proceeded to a large extent by the time we reach equilibrium. In a reactant-favored system, the reverse reaction predominates at equilibrium. Here's a sample AP problem to try on your own. Pause the video here and answer the question. When we come back, I'll reveal the answer. Welcome back. Here's what you should have gotten. Now a couple of notes on our equilibrium constant. First, if we're given an equilibrium reaction and then we change the coefficients of that equilibrium reaction as we have here, notice we started with 2A and 1B yielding 4C. We've essentially cut this reaction in half to have 1A plus 1/2 B yielding 2C. The equilibrium constant for the second reaction will be equal to the equilibrium constant to the first reaction raised to the power equal to the factor by which we changed the reaction. Since we multiplied reaction 1 by 1/2, we raised the K value to 1/2. Likewise, if you reverse a chemical reaction, you essentially invert the K expression, which means that your K value for the reverse reaction will be the inverse of the K value for the forward reaction. This also applies to Q values, which we'll look at in a future video. In some cases, we may add two reactions, each with its own K value. In those cases, the K value for our resulting reaction will be the product of the two K values for the reactions we added together. Notice we added the reactions, but we multiply the K values. Let's now look at equilibrium constants and equilibrium positions. Here we have a set of initial conditions before equilibrium is achieved. Then we have our equilibrium position, which is the set of concentrations at equilibrium, and our calculated K values for each system. Notice that in each case, the K value has remained relatively unchanged, though the equilibrium position is quite different. This tells us that even though the position is different, the ratio will remain the same to give us the same K value. Therefore, equilibrium position depends on initial concentration, while equilibrium constant does not. Let's review some final important notes about the equilibrium constant. At equilibrium, the concentrations of reactants and products are always present in the same ratio at a particular temperature, as we saw in the previous slide. This will result in the same K value for the system regardless of the amounts of reactants and products you start with, since the ratio will remain the same. This is only true as long as the temperature is held constant. Equilibrium constants also do not depend on equilibrium concentration, as we just discussed. It also doesn't matter which direction from which equilibrium is established. Whether you start with all reactant or all product, you'll still end up with the same ratio of reactants to products at equilibrium, so our equilibrium constant will be the same. And finally, the equilibrium constant is dependent on temperature. Change the temperature, change the equilibrium constant. That brings us to the end of this video. Let's review our goals. First, we looked at the difference between equilibrium constant, equilibrium expression, and equilibrium position. Then we looked at how to write an equilibrium expression for a reaction. Then we learned to calculate equilibrium constants for a system given equilibrium concentrations. And finally, we looked at the significance of the relative size of the equilibrium constant.